So, good evening, everyone. Uh, Today we'll be having a tutorial on how to do unsupervised learning. So, K-means clustering and PCA. Yeah, I hope my screen is visible. Okay. So, this is the notebook I have. You install some packages, load the basic packages like NumPy, plotting, data frame reading, and so on. Okay. We'll start with some data set. Okay. Before we do anything, we have to look at something called scaling of the data set. Okay. Yeah. Scaling of the data set. What do I mean by scaling is that your original data is between 0 to 10, or it's in like 0 to 1000 or minus 1000 to 1000. Okay. These are all huge, like big values that your model might not be able to handle. Okay. So what you do is before feeding your data into some model, you have to do something called scaling. Typically, it's you use the standard scaler where your data is mostly distributed between -1 and 1, most of the data. Okay. Or if you want it between 0 and 1, it's min-max scaler, or something called a robust scaler. I mean, very similar to the standard scaler. And also you have the normalizer. Okay. Typically, what you start with is the standard scaler because you subtract the mean and divide it by the standard deviation. Okay. And you can go with the min-max scaler or robust scaler, no issues, but the standard choice is the standard scaler. Normalizer, it will normalize the data across, not, it's not based on each feature actually. It will normalize across rows, and that is for a different use case that mostly you won't come across, so it should be fine. So we'll start with looking at how k-means clustering works. Okay. So you have some input data. How many clusters do you think there is? What can be the number of classes based on this data? How many clusters? Am I audible? Hello? Screen is also shared. Yeah. Okay, so there are three clusters. Okay. And what you do, how it k-means clustering works is that you start with any three random points as centroids, compute the distance, whichever is closest. Let's say this point is close to red, you assign it as red. And if it's close to green, you assign it as green. Then recompute the centers, keep reassigning, you keep doing this again and again until the clusters don't change. This is how k-means clustering works. You want to look at decision boundaries, this is how it is. Okay, anything that falls under this boundary is blue, here it's green, here it's orange. Okay. Any doubts how it works, how k-means clustering works? Okay, no doubts. So we'll start with some sample data set. Okay. and some synthetic data set. This is how you build a model. It's from a scalar.cluster, import k means. You have to mention the number of clusters beforehand. Okay. And if there is any other new data point, you can use the predict function and predict it. Okay, scikit-learn, typically this is the workflow. Before this, you can also include another standard scalar or something, but when you use some synthetic data from scikit-learn, most probably it should be standardized. Okay, this is how it looks like. If you change k, let's see what happens. I'm plotting for k2 and k5. Here 3, it's fine. Okay, but when it's 2, this doesn't look good. These are indeed two separate clusters. But then you only gave k as 2, so it's combining these two as one cluster and this as separate cluster. And when k is 5, it looks like this: 2 here and 3 here. Okay. As I said, k depends on your intuition. If you want 3 different check sizes or something, you have to mention 3, or if you want 5, you have to mention it as 5 and so on. Okay, now we'll look at a real life data set. Okay. Okay. This is a real life data set. Okay. Essentially, it's based on patient data where I mean, who have been hospitalized for depression. These are different features that have been calculated, and you sort of want to predict whether a patient is in depression or not based on these features. Okay. You drop the ID column because ID column is not a feature. You should do that. Then, if you put in the info function, you can get what are all the numeric and non-numeric columns. You can use the describe function to get the mean, standard deviation, and other statistics, okay, for all the features. And we can also do, so in the case of iris dataset, I said you can't visualize more than, so like 3 dimensions. Here you have 5 different features or 6 features. So what do I do? Iris dataset, when I showed something at the very initial slide, there was something called a pair plot. What does it do? Anyone? Okay, it's a pair plot where you plot pairs of features. Okay, and that is what I'm doing now. You see, this is the pair plot for, so there are 6 different features. It will be a 6 cross 6 matrix of plots. Based on this, you don't get any information. Like, okay, maybe this is one cluster, this is one cluster, or this is one cluster, and this is one cluster. I mean, or this is one cluster, this is one cluster. You can't make any conclusions. So first, I standardize the data, okay, using this function z-score, and I try different case, okay, and I sort of calculate the in minimum, like some square distance. Okay, that's what I'm doing. This is how it is. So as I said, you can't like keep 9 or you can't keep 1. You have to choose something in between. I can either choose 3 or 4. This is based on the elbow criterion that I mentioned before. Okay. So I'll set as 3. I'll fit it, and I'll plot and check how it is. Okay. Yes. Yeah, there is something wrong with the figure. Okay, maybe I'll fix this thing, but essentially it's 3D plot where you have different features. Okay. You can also get predictions using the predict function. Okay. You see, these are different predictions that you have based on each feature. So if it's higher in the middle one, it's for cluster one. So most of the points are in cluster one than cluster zero or cluster two. Okay, this is for each feature that you have. This is how you should interpret this. I can also plot the graph. You see, this is how it looks like. Three different clusters. But ideally, like these green things should come in blue, and this orange might be in green, but it's good enough. It doesn't matter. If you try it with two, that's a different thing. Sorry, I think this won't work. This I'll change. Yeah, it's not working. Do that later. Again, you can get predictions and get the graph like for each. This is for two clusters. Okay. This is also not good enough. Maybe you can try four and check how it is. Okay. That is an exercise that you can do. I'll share the data set. You can also do it on other data sets. It's called the digits data set where you have different sort of images. Okay. You have different images for different numbers from 0 to 9. And you have to sort of cluster based on these images. Okay. So 0 to 9. So totally there are 10 digits. What should be the number of clusters I should set? There are 10 clusters. What should be the k that I should set? There should be 10 clusters because there are 10 digits, okay? And you can do strain test split. I put n clusters as 10 and did the prediction. You can also evaluate performance. Like there are different scores. Like as I mentioned in the evaluation matrix case, you have homogeneity score, brand score, the confusion matrix, and so on. Okay. Um, You can also look at some failure cases. Like these are all failure cases. Okay. Like cluster one and two. This is sort of like a mixture, okay, that you see here. These things should be here and these things should be here. It should be assigned to a different cluster. But yeah, these are some, as I said, it's a failure case because based on the number of k that you choose, this entire interpretation can also change. Okay, and that shouldn't be like sort of happening in the ideal case. Okay, but this is what it is. It has some drawbacks. Okay. Any doubts in k-means clustering? No doubts. Then I'll move on.
No doubt.
Okay. Then I'll move on to PCA. Okay. Like this is the original data that you have. You transform it like this. This is only the second. This is only the second component. This is only the first component. Like as you can see, like combination of this one and this one can sort of like give you this data. Okay, that's how you should interpret it. Okay? I am taking some data set. Okay, it's called the wine data set. Again, you so based on the alcohol percentage, like different features, you have to predict whether it's some sort of wine or not. You have class labels. So this is how you split the data. These all should be your X. Class label should be Y. And that's what I'm doing here. Like the zeroth index is assigned to Y. Other than the zeroth index, everything else goes to X. Standardizing the data. This is how you standardize it using standard scaler. Because as you can see, like here, there is 14, there is 1, there are like different numerical ranges. Here is 1,000. So the model shouldn't be confused saying that, okay, this value is way higher than 14.23. So the model shouldn't be biased towards any feature. And that's why you're doing standard scaling. Do this, you calculate covariance matrix, okay, get the eigenvalues, eigenvectors, let me plot the variance explain. Okay. So as you can see, I had like around 14, 15, 14 different features. And as you keep increasing the number of components, the explained variance also increases. So ideally, you can take in this case like 10 features you can take instead of 14. Okay. But this is you can take two also, but the cumulative variance in that case is only around 60%. That's not good enough. So it's better you can take like something from 6 to 10. Okay, that should work. You can also do this using the PCA class and scikit-learn. Okay. And you can also, it's almost the same. This is what I did manually using linear algebra. This is what I did using PCA. I'll only take two components. Okay. I'm reducing from 14 to 2. And let me try visualizing it. This is how it is. Do you see any pattern here? Can you separate some like this data set into two classes? any patterns.
Yes, sir, it can be separated into two class, I think.
Okay, something here, but not exactly because there is something in the middle
Yes,
that
sir.
that's not very clear. That's why it's only 60%. Maybe if you had 90% here with two components, you might have been able to separate it properly. Okay. And this is the feature importance, like how each feature contributes to the first and second component. Okay. Like first component, like magnesium and total phenols have the highest sort of weights. In second component, it's proanthocyanins and OD 28315 ratio, and proline doesn't contribute to anything. So it's fine. Another data set, it's the breast cancer data set I have. I'll reduce it to two dimensions. I put n components as two. I fit, and then I transform, then I plotting. Again, it's not good enough separation, but it's okay. Okay, at least it's able to differentiate between the malignant and benign cancer case. And shape is two. Okay, number of data points times the number of components. Okay. What you can do then later is with this transform data set, you can do logistic regression. Okay. And you can sort of see that you get almost same score. Before PCA, the score was 0.959, almost 0.96. After PCA is also the same, almost the same. Okay. So that means I'm not losing much information. Even with just two features, I'm able to predict the class properly. Okay. And one thing you have to remember is the scaling and PCA transform that you do, it should be done after splitting the data set, not before splitting. Okay. This is one thing you have to remember, because if you do it before splitting, you can do something called data leakage, where information sort of leaks to the model, and the model can sort of predict based on the mean statistics and so on. And you don't want that. You don't want the model to cheat. Okay? And because if the model cheats, it will give you better accuracy, but when you deploy it in real life, it will sort of give reduced accuracy, and you don't want that. So this is the tutorial. I'll share the notebook now. You all can start working. Like what I want you all to do is try different k values for k means, try different n components for PCA, and if you have any doubts, you can let me know. Okay? Yeah, everyone try running the notebook. Any doubts, I can clarify. Okay?
So why scaling is after the data set returns?
No, so after splitting, you should do scaling, because beforehand, scaling what it will essentially do is you calculate the mean of the data and divide by the standard deviation of the data. Okay. But if you take the whole data set before splitting, like ideally, when a new data point comes, you don't know like the mean and standard deviation for that set of data. Okay. So you want to sort of have the same thing here. So what you do is from the train data, you calculate mean and standard deviation, and you apply the same on test data. Okay. But if you do that before splitting, what will happen is if you do scaling before, then do the splitting, it sort of leaks information. Okay. And you don't want that. Okay. So whatever is happening in real life, you have to make sure this happens the same here also.
Okay, sir.
So everyone start running the notebook. Any doubts? So are you able to run something?
So for K means the CSV file is not supported, sir.
Yeah, the depression.csv, right? That I'll upload it later. Okay.
Okay.
Okay, there are no more doubts. We can end today's. Tomorrow we'll start with neural networks. Okay, thanks. I'll also share the data set and slides.
Okay, sir.